Good morning to one and all. Today's topic is algebra of limits. Here we are going to prove one theorem. The statement of the theorem is as follows. Let f of x and g of x be two functions such that limit extends to a f of x equal to L and limit extends to a g of x equal to M. Then the following are true. First one, limit extends to a f of x plus g of x equal to L plus M. That means we are going to apply limit for f of x and limit for g of x separately. That means limit extends to a f of x plus g of x can be written as limit extends to a f of x plus limit extends to a g of x. This is, we know the value of this one, that is L. We know the value of limit extends to a g of x, that is M. That's why the answer is L plus M. Similarly, instead of plus, if we have minus, limit extends to a f of x minus g of x is L minus M. That means here also we are writing separate limit and substitute the values of limit extends to a f of x and limit extends to a g of x. So, limit extends to a f of x minus limit extends to a g of x. First one value is L, second one value is M. So, we are going to get answer as L minus M. Third one, limit extends to a f of x into g of x equal to L into M. That is, LHS can be written as limit extends to a f of x into limit extends to a g of x. We know both values. Substitute, then we are going to get L into M. Fourth one, limit extends to a f of x by g of x equal to L by M. That means apply separate limit for numerator, that is f of x, separate limit for denominator, that is g of x. Substitute the values, then we are going to get L by M. Here they are given one condition, that is M is not equal to 0. If M equal to 0, then L by M becomes L by 0. That means we are going to get infinity. To avoid this infinity, we are taking M is not equal to 0. Now we prove all these four by using the definition of limit of a function. Proof. By data, limit extends to a f of x equal to L and limit extends to a g of x equal to M. This is, we know. Now we are going to prove limit extends to a f of x plus g of x equal to L plus M. For this, we are going to use limit of a function definition. Here we have limit extends to a f of x equal to L. Implies by using the definition of a limit of a function, we can write for every epsilon greater than 0, there exists a real number delta 1 greater than 0 such that modulus of f of x minus L less than epsilon by 2 whenever 0 less than x minus A less than delta 1. Why we are taking here epsilon by 2? In the definition here we are going to get epsilon only. But in this situation I am taking here epsilon by 2. Why means at the end I need epsilon. For that purpose I am going to take epsilon by 2 here. Take this as equation 1. Again, limit extends to a g of x equal to M again we are using limit of a function. Definition of limit of a function. For every epsilon greater than 0, there exists a real number delta greater than delta 2 greater than 0 such that modulus of g of x minus m less than epsilon by 2 whenever 0 less than mod x minus a less than delta 2. Take this as equation 2. Let delta equal to minimum of delta 1 and delta 2. That means if delta 1 equal to 2, delta 2 equal to 3, then minimum of these two is 2. That means delta equal to 2. Now equation 1 and equation 2 I am going to rewrite. Modulus of f of x minus L less than epsilon by 2 and modulus of g of x minus m less than epsilon by 2. For 0 less than mod x minus a less than delta. Here you can observe in equation 1 we have delta 1, in equation 2 we have delta 2. Whenever I take delta as minimum of delta 1 and delta 2, then I am going to replace delta 1 and delta 2 by delta. Now consider modulus of f of x plus g of x minus L plus m. This is equal to, now I am multiplying with minus, then minus L minus m. Here you can observe minus L minus m. Positive f of x, positive g of x. Now I am going to write modulus of this quantity as less than or equal to modulus of f of x minus L plus modulus of g of x minus m. By using standard properties of modulus, that is modulus of a plus b less than or equal to mod a plus mod b. Here I am taking this as a, this as b. So mod a plus b less than or equal to mod a plus mod b. Next, by using this concept, this one is strictly less than epsilon by 2 plus, again by using the same concept, again modulus of g of x minus m is less than epsilon by 2. So after substituting the values of these two moduluses, I am going to get this value is strictly less than epsilon by 2 plus epsilon by 2. But we know that epsilon by 2 plus epsilon by 2 equal to epsilon. That means take LCM, that is 2. In the numerator, we are going to get epsilon plus epsilon, that is 2 epsilon by 2. 2 to get cancelled, then we are going to get epsilon. For mod 0 less than mod x minus a less than delta. Thus, for every epsilon greater than 0, there exists delta greater than 0 such that this LHS value strictly less than epsilon. I already informed during these steps, if we get epsilon in one less than in one place, finally we get less than only. For 0 less than mod x minus a less than delta. Observe, this is the definition of the limit of a function. Then limit of this equal to limit of this equal to L plus m. Therefore, we can prove that limit extends to a f of x plus g of x equal to L plus m. Second one, limit extends to a f of x minus g of x equal to L minus m. Here also we are using limit of a function definition. Observe, whenever we have this one, we can write this line. Whenever we have this, we can write this. Okay, here we have f of x is, we can write f of x adjacent to limit L as RHS. Here x tends to a as x minus a. So we can write whenever this term, we can write this by using the definition of a limit of a function. Observe, limit x tends to a, f of x minus L implies for every epsilon greater than 0, there exists a real number delta 1 greater than 0 such that modulus of f of x minus L less than epsilon by 2 whenever 0 less than mod x minus a less than delta 1. Here also I take epsilon by 2 because at the end I want to get epsilon. Again, limit x tends to a, g of x equal to m implies for every epsilon greater than 0, there exists a real number delta 2 greater than 0 such that modulus of g of x minus m less than epsilon by 2 whenever 0 less than mod x minus a less than delta 2. Here we take delta 1, that's why I take delta 1 here. Here I take delta 2, that's why here delta 2. These two lines are on the basis of definition of the limit only. Once again, f of x comes here, L comes here, modulus of f of x minus L less than epsilon by 2. Here we have x tends to a, that's why modulus of x minus a. So you can practice whenever we have this one, you can practice to write these lines. Whenever you have these lines, you can practice to write this one. Again, next, let delta equal to minimum of delta 1 and delta 2. So whenever we take delta as minimum of delta 1 and delta 2, we can replace delta 1 and delta 2 by delta. So observe, equation 1, equation 2, these two are not changing because here we are not getting delta. Here only instead of delta 1 and delta 2 I am replacing with delta. Next, now consider modulus of f of x minus g of x minus L minus m. Minus into L minus L minus into minus m is plus m. F of x as it is minus g of x as it is. Next we are taking this as a, this as b. By using the properties of modulus, we can write this modulus is less than or equal to modulus of f of x minus L plus modulus of m minus g of x. Next line, I already informed to you, inside the modulus we can easily change the terms place, that is m minus g of x can be written as g of x minus m because modulus of 4 minus 5 is equal to modulus of minus 1, that is 1 only. Similarly, modulus of 5 minus 4 is also equal to modulus of 1, this is also 1 only. That's why here I am interchanging these two terms, that is m minus g of x, modulus of m minus g of x is nothing but modulus of g of x minus m. But we know this value and this value, that is epsilon by 2, epsilon by 2. So first one is less than epsilon by 2 plus second one is also less than epsilon by 2. But epsilon by 2 plus epsilon by 2 is equal to epsilon for 0 less than mod x minus a less than delta. Thus, we have for every epsilon greater than 0, there exists delta greater than 0 such that modulus of f of x minus g of x minus L minus m less than epsilon. Why here less than epsilon means here we are getting less than. During this process, once we get less than, and in the final step we can write less than only. For 0 less than mod x minus a less than delta. So this is the definition of a limit of a function. then we can write limit x tends to a, f of x minus g of x is equal to L minus m. So the proof of second one is completed. Now we are going to prove third one, that is limit x tends to a, f of x into g of x equal to L into m. Proof, here we are taking epsilon 1 is a given quantity which the value of epsilon 1 lies between 0 and 1. So epsilon 1 is also positive. Here we are taking limit x tends to a, f of x equal to L. This is given one only. Now I am writing this line by using the definition of a limit of a function. Previous two problems, in previous two cases I am writing here epsilon only, but in this case I am taking epsilon 1. So by using the definition of limit of a function, for every epsilon 1 greater than 0, there exists delta 1 greater than 0 such that modulus of f of x minus f of x minus L less than epsilon 1, because here we are taking epsilon 1. Whenever 0 less than mod x minus a less than delta 1. Similarly, limit x tends to a, g of x equal to m implies for every epsilon 1 greater than 0, there exists a real number delta 2 greater than 0 such that modulus of g of x minus m less than epsilon 1. Whenever 0 less than mod x minus a less than delta 2. Take this as 1, this as 2. Let delta equal to minimum of delta 1 comma delta 2. Then from 1 and 2 we have this is 1, this is 2, but instead of writing delta 1 and delta 2 we are writing delta only. Again, now I am going to find out the value of modulus of g of x. Here I am writing minus m plus m. That means the value of mod g of x does not change. The form of mod g of x is changed. If we are going to cancel these two, then we are going to get mod g of x only. Here again I am using the same concept. This is I am taking as a, this as b. So a modulus of a plus b less than or equal to mod a plus mod b, which is strictly less than 1. Why 1 means here we have modulus of g of x minus m is less than epsilon 1. Modulus of g of x minus m is less than epsilon 1. But at the starting we are taking 0 less than epsilon 1 is less than 1. So epsilon 1 is less than 1. So I am taking this and this. So modulus of g of x minus m is less than m. Mod m as it is, plus also as it is. For 0 less than mod x minus a less than delta. Now consider modulus of f of x into g of x minus Lm. Here also I am writing f of x into g of x here minus Lm here. I am adding and subtracting L into g of x. So the form does not changes, only the value does not changes, the form only changed. So observe these two terms. G of x is common, so remaining terms are f of x minus L. Here L is common, remaining terms are g of x minus m. Here I am using the same concept, that is modulus of a plus modulus of b. Modulus of a plus b is less than or equal to mod a plus mod b. And also one more concept, that is mod ab equal to mod a into mod b. By using these two, I am writing one modulus for this one modulus for this one, and again separate modulus for this, this and this. Then we are going to get this step. Here observe, we can already have modulus of g of x is strictly less than 1 plus mod m. This one is strictly less than epsilon 1 plus mod L as it is. This is strictly less than epsilon 1. For 0 less than mod x minus a less than delta. Observe, mod g of x is strictly less than this 1 plus mod m. Modulus of f of x minus L is less than epsilon 1 mod L as it is. Modulus of g of x minus m is less than epsilon 1. Now I am choosing epsilon 1 equal to epsilon by 1 plus mod m plus mod L. Where epsilon is a given positive number, this is very small positive. So substitute this epsilon 1 value here. Observe, here we have epsilon 1 is common. Then 1 plus mod m plus mod L into epsilon 1. Now I am choosing epsilon 1 as, this one is as it is. The value of epsilon 1 is epsilon by 1 plus mod m plus mod L. So cancel this denominator with this numerator, then we are going to get epsilon. For 0 less than mod x minus a less than delta. Therefore, limit x tends to a, f of x into g of x equal to Lm by using the definition of a limit of a function. So, third one is also completely proved. Next, fourth one, limit x tends to a, f of x by g of x equal to L by m if m not equal to 0. I already explained why we are taking m not equal to 0. So, proof of fourth one is as follows. First, we show that limit x tends to a 1 by g of x equal to 1 by m. Again, by using the definition of a limit of a function, we have this one, we can write this one. For every epsilon 1 greater than 0, there exists a real number delta 1 greater than 0. Here whatever you can take, those values are compulsory greater than 0, such that modulus of g of x minus m less than epsilon 1, modulus of x minus a is less than delta 1. Consider mod m. Here I am writing mod m as mod m minus g of x plus g of x. Here the form is going to change, but the value is not changing, which is less than or equal to m into m minus g of x, because I am using same concept. Modulus of a plus b less than or equal to mod a plus mod b. But I already informed to you, inside the modulus we can easily change the terms. So m minus g of x can be written as g of x minus m mod g of x as it is. But we know this value is less than epsilon 1 mod g of x as it is for 0 less than mod x minus a less than delta 1. So observe this one, what we get, mod m is less than epsilon 1 plus mod g of x. So take this epsilon 1 this side, then mod m minus epsilon 1 less than modulus of g of x. Whenever we are changing the places, less than becomes greater than. So modulus of g of x greater than mod m minus epsilon 1. Then we are going to get this step. Let us choose epsilon 1 equal to mod m by 2. Then we have modulus of g of x is greater than mod m by 2. Because observe, here we have epsilon 1 is mod m by 2. So that is m is a positive quantity. You can treat this as m by 2 only. So m minus m by 2. this is m by 2 only. That means 1 rupee minus 50 paise is 50 paise only. Whenever we choose epsilon 1 as mod m by 2, then we are going to get mod g of x is greater than mod m by 2 for 0 less than mod x minus a less than delta 1. That is reciprocate. Now we are going to reciprocate this LHS. That means modulus of g of x by 1 can be written as 1 by modulus of g of x. Whenever we are reciprocating, less than greater than becomes less than. Here also we want to reciprocate. That means denominator becomes numerator, numerator becomes denominator. This is same condition carries. Again, limit extends to a g of x equal to m. Again, by using the definition of a limit of a function, we can write for every epsilon 2 greater than 0, there exists delta greater than 2 0 such that modulus of g of x minus m less than epsilon by 2 whenever 0 less than mod x minus a less than delta 2. Take delta as minimum of delta 1 and delta 2, then this one can be written as is and this one also as is, but instead of writing delta 1 and delta 2, we are writing delta. Now consider modulus of 1 by g of x minus m. Now we want to show that this one is less than epsilon. So take LCM m into g of x, then we are going to get m minus g of x. Separate modulus for numerator and denominator because mod a by b is equal to mod a by mod b. So again in the denominator mod ab equal to mod a into mod b concept. By using these two concepts, this term is converted as like this. And also we know that inside the brackets, inside the modulus, we can change the place of the terms. That's why m minus g of x becomes g of x minus m. So this numerator is, observe, modulus of g of x minus m is less than epsilon by 2. This mod m as it is, modulus of g of x 1 by, here 1 is there, 1 by modulus of g of x is less than 2 by mod m. Okay. Otherwise you can write this as modulus of g of x minus m divided by mod m into 1 by mod g of x. So 1 into anything is this one only. This one is less than epsilon by 2. Mod m as it is, 1 by mod g of x is less than 2 by mod m. So we are going to get clear idea. So here epsilon 2, now I am going to choose epsilon 2 less than mod m square by 2 into epsilon. Why I am choosing like this means at the end I want to get epsilon only. Where epsilon is a given positive number, however small, substitute epsilon 2 here value. Observe, here we have epsilon 2 by mod m into mod m is mod m square. If I choose epsilon by 2 as like this, that means mod m square by 2 into epsilon. This one as it is. So just I substituted epsilon 2 value. This 2 cancel. This 2 cancel. This mod m square cancel. Then we are going to get epsilon. To get epsilon only, I choose epsilon 2 like this. So this one is less than epsilon for 0 less than mod x minus a less than delta. So again by using the definition of a limit extends to a 1 by g of x equal to 1 by m. Now multiply both sides with f of x. Then we are going to get here f of x. Then this one can be written as limit extends to a f of x into 1 by g of x. Now by using the concept 3, we can write separate limits for this one and first f of x and 1 by g of x. We know limit extends to a f of x is L. This one is just now we proved equal to 1 by m. 1 into L is L, L by m. Finally, limit extends to a f of x by g of x equal to L by m. So, 4 conditions are, otherwise 4 properties of limits of a function completed. That means algebra of limits completed.